so now let's talk about similarity. Right, so here's what similarity means and what similar figures are. If two figures are similar, then they have the exact same shape, but not necessarily the same size. And we're going to go into some more detail about what we mean when we get to different polygons, triangles, things that were a little bit more specific. Right? So here's a very simple example. I'm going to use my shape tool here, right? And I'm going to draw myself a heart. Okay? So this is a shape, okay? And what we're claiming is that we can compare this to another shape, right? Right now the shapes are congruent. Congruent means exactly same size, exactly same shape. So what we're going to change now is we are going to change the size of this one. So I'm going to make this one smaller, okay? It's still a heart. It's the same shape. But now it's way smaller. It's not the same size. And so what we'd say is that these two hearts are similar instead of saying they are congruent, because they're not the same size anymore. They're not congruent, right? And we have this symbol, right, which is kind of a part. Remember, our congruent symbol was an equal sign with this little squiggly line on top, right? We're going to take away the equal sign because we're not congruent anymore, right? So we're going to say this one's got to go. But we're going to leave behind the squiggly line, and we're going to say that these two hearts are similar to each other, right? Because they are the same shape. They're both hearts, but they are not the same size because the one on the left is bigger and the one on the right is smaller. Okay? So let's keep going with this idea. And let's talk about polygons. So we're going to actually be a little bit more specific about what has to be true if polygons are similar. Okay? If polygons are similar to each other, then two things are true. All of the corresponding angles are congruent, okay? And all of the lengths are proportional. Right? So this is the change. Now all of a sudden all of the sides aren't equal. All of the sides are proportional. So let's take these two shapes. I'm claiming that these are similar, but we're going to actually prove it. Right? And we're going to come up with this thing called a scale factor, which is kind of a number that's going to describe how much bigger or how much smaller the value got. Right? So if you remember from dilations, we had a scale factor. So we're going to find that value. So the first thing I'm going to do is I'm going to check the first one, and that's that the corresponding angles are congruent. So I have my protractor here. And I'm going to drag it, and I'm just going to do a quick check on my angles here. So if you notice this first one, if I'm using my protractor correctly, it looks like it's going up to a little bit more than a little bit less than 110 degrees. This angle is about 110. If I come over to this shape, I can measure this one. And if you notice, I'm getting pretty much the exact same thing. When I go right here, it's a little bit more than 110 degrees. All right, so I'm going to check one more. We're not going to check all three, but you'll get the kind of the idea. So I'm going to just turn this now, and I'm going to check this this angle up here. All right, and I'm going to do the same thing, and I'm going to say this angle, it looks like is a little bit more than 30 degrees. And if I come over here, I can do the same thing. And I can check and say this one is exactly in the same spot, a little bit more than 30 degrees. And so then the third ones would also have to be equal because we've just shown that the first two are. Right? So I can prove that for these two shapes, these two triangles, that all of the angles are congruent. They're all equal to each other. They're the same size. Okay? So now here's the different part. Now I got to bring my ruler because I got to measure the sides. Okay, so I'm going to start off by measuring these two sides here. And if you notice, this one is, and I'm going to write these down because we have to compare them. Okay, let me get rid of my protractor. All right, I'm going to say that the first set of sides here, if I go from end to end, okay, let me be really careful. We want to be as accurate as we can be with our measurements. Right, that these two are about 5 points. This one is about 5.7 centimeters long. Okay, so I'm just going to use 5.7. Okay, I'm going to compare that to the other triangle. Right? And if this one, if you notice, it's about 3.6 centimeters long. Which again, I'm just going to write the 3.6. Okay, and then I'm going to check the other sides. And so what has to be true is all of these have to really represent the same fraction. So let's check this bottom one. Okay, so I'm going to check this one now, and we're going to go to the edge, and we're going to say this one looks like it's about 4.7, okay, the big one, right? So if you notice, I had the big one on top, so I'm going to keep saying the big one should be on top, about 4.7, and then I'm going to go over to the small triangle, and we're going to check that one, okay, and this one looks like it's about, about 2.9 centimeters long, so we're going to estimate about, as closely as we can, about 2.9, okay, one more, right, that we got to check, so let's check the kind of angled side over here. So we'll check the big one first. Okay. And so in this one, it looks like, let me straighten out my ruler a little bit. Okay. It looks like this one is about 8. Oh, not even all the way to the top. A little bit more than 8. We're going to go with about 8.3, about 8.2, we'll say. Okay. About 8.2 centimeters long. Okay. And if I do the same thing for my smaller one, okay, let's check again, try to be as accurate as we can be. It looks like it's about 5.2 centimeters long. Okay, so I'm going to pull out my calculator, and we're going to turn these all into decimals and figure out what the decimal equivalent is, because it's tough to reduce these ones. So if I do 5.7 divided by 3.6, okay, it looks like these are about 1. This fraction means about 1.58. Okay, rounded to the nearest hundredth. Let's check the next one. 4.7 divided by 2.9. Okay, this one's a little bit bigger. This one's saying 1.62, but remember, I'm estimating here. Okay, and if you notice, let's see what the third one comes out to be. Let's see what the third one comes out to be. I'm going to go back to my calculator. About 8.2 divided by 5.2. Right? Well, let me try that again. My calculator's being funny. 8.2 divided by 5.2, and it comes out to be about also 1.58. Right? So I'm guessing that I probably had a little bit of a rounding error here. This might have been like 2.8 instead of 2.9. So let's check real quick. If I try this instead of 2.8 instead of 2.9, if I do 4.7 divided by 2.8, okay, nope, wrong way. Okay, maybe it's about 4.6. But anyway, I have a little bit of a rounding error here, but you get the idea. This one came out to be 1.58. If I had it measured correctly, which I probably made some small mistake with my measurement, that would have been 1.58. This one's also 1.58. And so we're claiming, assuming that I did this one correctly, that these are all about the same proportion. Okay, again, with rounding and then with to the nearest tenth, they're pretty close. If I round to the nearest tenth, this is 1.6 and 1.6 and 1.6. So since I kept these ones to the tenth, let's do that. We're going to say this is really 1.6 and 1.6 and 1.6. Okay, so that we can have a very close estimate, right? So when we're measuring to the tenths, it's helpful to also keep our scale factor to the tenth. So I'm going to come down here, and they're going to say the scale factor. So here's what this one's saying. We measured the big one to the small one. That was the order that we did them. So I'm going to claim that my scale factor is 1.6 centimeters of the big one is the same as 1 centimeter of the small one. This is my ratio of big to small. Right? So I would say my scale factor here is about 1.6 centimeters to 1 centimeter if I'm comparing these. And these are similar shapes because I measured the angles and they were all equal to each other. And I measured the sides and they were all proportional to each other, right? They all came out to be about 1.6 as a common ratio. Okay, so we can take a look, okay, at some problems and say, are these proportional, right? So in this one, they've done all the measuring for us, so I can take a look at this and just say, okay, let's see. They're showing me this arc and this arc are equal, so that's equal angle, equal angle, equal angle. All four of the angles are equal. They are showing me that in the picture with the markings, and so I'm going to say, all right, first criteria is true. It looks like the angles are congruent. So I'm going to just put a checkbox there. Okay. Compare the ratios of the corresponding sides. So between the double arc and the single arc in the big, what looks like the bigger one, right, I'm going to say is a 6. And I'm going to compare that to the smaller one, which is also a 6. And I'm going to do that for all of these. This one is 12 over 6. Okay. And then I got 24 over 16. Okay. And on the kind of this longest side, I have 24 over 14. Okay, so you can kind of look at these and say, you know what? These are not similar because this represents 1, this represents 2, this represents some number between 1 and 2, this represents a different number between 1 and 2. That we're going to say no, these are not similar polygons because they do not have the same ratio when I set up corresponding sides in a fraction. Right? And so that's the basic idea of determining whether polygons are similar to each other. We're just going to compare the sides and we're going to say yes they are or no they are not similar to each other.